most comprehensive preparation platform, that is the Byju's exam prep, and welcome once again to the Formula 1 series. Yes, and this is the digital electronics formula session part number 2. Yes, guys. This is the part number 2 of the digital electronics because the students were demanding lots of formula. And in the first session, we covered up some of the topics of digital. The first session that we took on Friday, and this is the next session, and we are going to continue with the most important formula for your Gate 23 examination. This particular Formula 1 series, of which is going to give the formula of all subjects. Right now, we're in digital electronics. Yesterday, you had analog electronics as well. Here, we are discussing a very, very important formula required for your revision cycle. Yes, guys, it's almost 18th October. You can say October end, and the time. Okay, it's already started, so that you start revising the things, and especially when you enter the December and January, you will be revising. Voice is too low. Yes, guys, quickly confirm everybody regarding audio, video, everything is clear to all or not, so that we can, quickly begin this discussion. So what I'm telling is December, January, again, you have the complete revision cycle coming. So there, of course, we know that GATE is a conceptual examination. You need to focus more and first on the concepts. But after having thorough understanding of concepts, it is important to accumulate and gather all the formulas in one place. And that is what this session is going to do you. That is what these sessions are going to do you. They are just going to complete your formula book. Very, very good evening all. Keep joining the session. Okay, students are slowly joining. But anyways, let's get started. And this is a brief intro about me in case somebody new to my session. This is your mentor and educator Rakesh, and I have secured All India rank 9 in the GATE examination. Completed my masters from Indian Institute of Science, Bangalore. It's been more than 12 years. I've trained more than 50,000 students in my journey, and this is what is my major area of expertise, as you're able to see on the screen. Okay, sure. Yes, guys, the All India Open Mega Mock. Yes, Byju's exam prep brought you the All India Mega Mock, and that started from 12th October and is going to be live till 19th October. That is tomorrow. Right. Yes. So tomorrow, 19th October, still is the last date where you can appear in this All India Open Mega Mock. Please appear. Do not worry that whether your subjects are completed now, whether your syllabus is 100% completed now. See, guys, if your syllabus is not completed, there will be several thousands of other students whose syllabus is not complete. They will be having similar status. The only thing is, right now, if you compete among thousands of students, where are you standing? Right, that idea you will get. Okay, that performance analysis you will get. So do not forget to appear. Register on the Byju's exam prep for this particular examination. And other than that, if you want to get the full-fledged test series for GATE, engineering services, and even other PSU exams, the Byju's exam prep has brought you the test series at very affordable prices. Okay, you can go and check the prices and the details of these tests, the schedule of the test on the Byju's exam prep app. The app is available on the Google Play Store. Good evening, all. Very, very good evening. Good evening, Sri Lakshmi, Shiva, Pankaj, Ravi. Okay, so let us get started, guys. In the last session of the digital, we have covered up the basics of digital. Then we went to, logic circuits. Then we talked about Boolean functions, min terms, max terms, minimizations, then K-maps, prime implicants, all those stuff we were just covering, and some, basic formula and techniques. Now, digital is a subject where I told you, sometimes there may be formula, but less number of formula. But rather than that, there will be techniques, there will be results to remember. So accordingly, this formula session, okay, it is named as formula, but it is like summary of the subject. Some topics may require formula, some may require truth table, some may require result to be remembered. So we'll keep focusing. So let us get started with the discussion of some of the important formulas from the combinational circuits. We all know what half adder is. It is a circuit which is used to add two single bits, right? For addition of two bits, two binary bits A and B, right? So of course, when you add 0 and 0, the sum is 0, the carry is also 0. When you add 0 plus 1, the sum is 1. There isn't any carry. 1 plus 0 is also 1. But when you do the mathematical addition of 1 plus 1, of course, 1 plus 1 is 2. In decimal, it is 2, right? Okay, if you have studied once, see Shiva, if you have studied once, then it is going to help you. See, GATE is never an examination where you start only with formula, to be very honest. Okay, so if you have studied once, and then this is definitely going to summarize your entire, most of the important topics. Okay, coming to that also, Gopi. Okay, so 1 plus 1 in binary, it is 1 0, right? So this becomes the sum, and what happens to this one? It appears as the carry that is going to be added at the next stage, right? So when you add 1 plus 1, the sum is 0, the carry is equal to 1. Okay, now this is the truth table for a half adder. We can just derive the Boolean expressions from here. Yes, sum is high at 0 1 and 1 0. That is the XOR combination. Carry is high when both the bits are 1 1. That is the AND gate actually. That is the AND gate actually, right? So, oh sorry, it is not mentioned. So I'll write down here. I'll write down these logic expressions here very clearly. So what do you have? The sum is nothing but A XOR B. And what is the carry? It is nothing but AB. That is the functionality of AND gate. That is known as the functionality of AND gate. So moving ahead to the next. Full adder. Now, as you know that carry is generated in most of the stages, and when you go for the next stage of addition, suppose 1 plus 1 is 0, carry 1. But here also if you want to add 1 0, if you do only using the half adder, you are not able to add this carry. Okay, so when you are adding suppose n bits of information, you are adding to 4-bit numbers, you are adding to 8-bit numbers, definitely this carry has to be used in the next stage of addition. Whether there is carry or not, initially we don't know, but we can assume that there will be in general carry. So we need to have a design which is not only going to add 2 bits of information, but that is going to add 3 bits of binary info, 3 binary bits, and that is the full adder. That is the full adder, right? Okay, so that is going to perform the addition, you can say, for A plus B plus C in. Okay, let me call this as C in. This is the carry coming from the previous stage. Okay, this is the carry coming from the previous stage. Okay, so A, B, C. Let me call this C. Let me call actually this C as C in. And let me call this carry as actually C out. Okay. Now, after the addition, that will also produce some carry and sum. Na? So, accordingly, this truth table is there, right? And once you look into the truth table, let's quickly revise the formula, not the truth table, but it is easy. Whenever 0 plus 1, it is just 0 plus 1, answer will be 1. But once you take this 0 plus 1 plus 1, so it is 1 plus 1. 1 plus 1, as I already explained you, sum is 0, carry is equal to 1, and etc. If you go to the last stage, isko thoda sa uplift karte hain. That is okay. If you go to last stage, 1 plus 1 plus 1, what is the result of 1 plus 1 plus 1? 1 plus 1 plus 1 is 1, 1, 3. 1 plus 1 plus 1 is 3. 3 in binary is 1, 1. So this becomes the actual sum, and this is what is going to go for the next stage of carry. So carry out will be 1. So 1, 1, 1, both will be 1. If you look into the logic functionality very clearly, what is going to be the answer? The sum is high at what? The sum is high at what places? 0, 0, 1, 0, 1, 0, that is 1 and 2, and then 1, 0, 0, which is 4, 1, 1, 1, which is 7. So when is the sum high? Let us write down. Achha. When is the sum high? Let me take the particular background only. So what is the logic expression for the sum? Sum is representing the 3-input XOR. Why it is 3-input XOR? Because last class only I explained you. Sum is high at the min terms 1, 2, 4, 7. I told you this is very important numbers for you to be remembered. Okay, sum of the min terms 1, 2, 4, 7 is nothing but the 3-input XOR as we already discussed. Okay, talking about the carry, talking about the C out is high at, look into this, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. That is 3, 5, 6, 7. Okay, so this is given by the formula summation of the minterms 3, 5, 6 and 7. 3, 5, 6 and 7. After feeding into the K-map, we all know the K-map, we are not deriving anything here. We are in this session, we are only focusing on the important bullet points and the final results. Okay, so from the K-map, when you simplify this, right, from the K-map, when you simplify, you get the expression which is going to be AB plus BC in plus AC in. AB plus BC plus AC. That is what is going to be the minimized expression for carry out. But although there is one more important expression for carry out. There is one more important expression for carry out. This is summation of 3, 5, 6, 7. Right. If I don't minimize using the K-map. So 3, 0, 1, 1, A bar BC. Right. 1, 0, 1. 1, 1, 0. 1, 1, 1. Okay, if I don't minimize using the K map, if I do a rough analysis here, from the first two term, C in is common, right? And if you take the C in common, you are left with A bar B plus A B bar, that is nothing but A XOR B. So this is A XOR B into C in. From the last two term, you have AB common, C plus C bar equal to 1. C plus C bar equal to 1. So this is one more expression for C out, and using this expression of C out, we are able to easily implement a full adder using only half adders. How? Using only half adders. How? See, everybody try to recall what was the half adder. Half adder has two outputs, sum which is A XOR B, carry which is A into B. Right. This is also a common pattern and common result to remember. How do you implement full adder using half adder? If you use this result, the hardware will be more. That is why I have applied some basic Boolean law rather than the K map, and look into this. This is AB. If I want to specify, this is what is one half adder stage. Can I say? This is one half adder stage because here this gate produces A XOR B, which is the sum output, and this is producing AB, which is the carry output of a half adder. So this one stage is the half adder. Again, if you talk about this particular stage, isko dhyan se dekhiye. This is again the same structure. This is another half adder. Now actually what do you want? You want the sum as A XOR B XOR C. So dear, A XOR B is already available. You have to take one more XOR gate, and then this XOR gate, what is fed? Look into this. C in. What is fed? That is the C in. So this produces the final sum. Right. What else do I need? I need the carry. A XOR B into C plus AB. Matter is AB is also available. A XOR B is also available. Sir, A XOR B is also there, AB is also there. I have to just do one thing. Multiply A XOR B by C. AND gate. AND gate is also there within the half adder. AND gate is also there within the half adder. Look into this. Right. Look into this. Yeah. I have to just multiply C. This is the C in. I'll just write down here. This is the C in. And what is this? This is A XOR B. This AND gate is already within the half adder. It multiplies the C in A XOR B. Next step is what? C in into A XOR B plus AB comes here, and this is the C out. Okay, ये K map वाला expression should not be actually written here. Let me remove that. I don't want this part. We have implemented the C out as we have simplified by the Boolean laws, right? Okay, so one full adder, I can say one more important result to note for you. Is two half adder plus one external OR gate. One full adder is two half adder plus one external OR gate. ठीक है? चलो. Right. Very quickly and in very brief, important bullet points we will keep revising. If you have any doubts, please do ask me. Right. Now using this, we build up the regular adder. Now this is a single stage addition. Now suppose, okay, I am adding two 4-bit of numbers. I am adding to 4-bit of numbers. Suppose this is the case. What should be the result? What will you do? You will start with this stage of addition. Initially the carry is 0. So 0 plus 1 is 0. Sum 0, carry 1. Okay, so every stage will produce a carry that has to go to the next stage. That should go to the carry input of the next stage. 1 plus 0, sum is 0. Sorry, 1 plus 0, sum is 1. But there is no carry. Again I say, there may be carry, there may not be carry. But in general, the carry output, every full adder will have a carry output, right? And every full adder will have a carry input as well. A, B, C in, sum and carry output, right? The carry output of every full adder should go to the carry input of the next full adder. The carry output of every full adder should go to the carry input. Like this, produce the carry, it should appear here. This also may or may not produce a carry, it should appear in the next stage, and etc, etc, etc. So if you want to build a 4-bit adder or an 8-bit adder or in general n-bit adder, what you have to do? You have to just connect. Suppose n-bit adder, you have to take n full adder. 4-bit adder. How many full adders? One full adder for this stage, second full adder, third full adder, fourth full adder. How many full adders will be required? Fourth, right? Feed the inputs AB directly to the individual full adder. The carry output of every full adder will go to the carry input of the next full adder. This is what is the design. We call this as parallel adder, or also known as ripple carry adder, right? This is the ripple carry adder, also known as parallel adder, because you apply all the AB bits, A0, B0, A1, B1, A2, B2, etc., etc., etc. Here the problem statement is something like this. You are adding two numbers A and B. You are adding two numbers A and B. A is 4-bit number, A3, A2, A1, A0. B is also 4-bit number, B3, B2, B1, B0. Right? When you add A0, B0, it produces the sum S0 and it produces the carry C1. Right? Here the initial carry was C0. Look into this. This is the first full adder. In this first full adder, the initial carry is C0, and then you feed the bits A0, B0. It produces the sum C0, and it produces the carry which should go to the next full adder, isn't it? The carry of every particular full adder, that's what I explained you, should go to the next full adder. Should go to what? Should go to the next full adder, correct? Okay, now this will be added, C1 plus A1 plus B1. This is added in the next full adder. It produces the sum S1, carry C2. C2 plus A2 plus B2, sum is S2, carry C3. C3 plus A3 plus B3, sum S3, and sum carry C4. That is the final carry. That is the final carry. This is what is the simple design known as the parallel adder or ripple carry adder. Why ripple carry adder? Because carry ripples. Carry moves from the LSB full adder to the MSB full adder. It is the wave propagation type of action. A disturbance, a carry applied here, keeps on propagating throughout the system and reaches to the MSB. So carry ripples from the LSB to the MSB. Okay. Advantage of this is simple and very, very easy design. Okay, this is the design of how you actually add the numbers, but disadvantage is it is a slow adder because this is only 4 bits. Suppose you have a 256-byte adder. The carry has to propagate. Delay hoga nishu. The carry has to propagate from LSB to MSB. Higher the number of bits, higher will be the waiting time, because the carry has to propagate all the way from the LSB to the MSB. Unless and until the carry propagates to the MSB, we can't decide what the final sum is. Okay. Right. So, how much is the total delay? Let us know derivation, but let us write down the formula for that with this example. What is the formula? What is the formula? Let me write down. If it is an n-bit adder, if it is an n-bit ripple adder, if it is an n-bit ripple adder, okay, the total propagation time, TPD, right, propagation delay, worst case propagation delay, total or also known as worst case propagation delay is given by the formula n minus 1 TC, where TC is the delay for carry, plus max of last stage ka TC or TS, max of TC TS. Okay, it's simple to understand, but let's not talk about the derivation. Let us focus on the numerical. So what does this question say? Right. Pragyan, Megamax solutions, the live video solutions are going to start from tomorrow itself. Pragyan, if you want the live video solutions, the solutions are starting tomorrow itself. Okay. A 16-bit ripple carry adder is realized using 16 identical full adders as shown in the figure. The carry propagation delay of each full adder is 12 and the sum propagation delay of each full adder is 15. What is the worst case delay of this 16-bit adder? What is the worst case delay of this 16-bit adder? So answer is TPD here, total propagation delay is n minus 1. It is a 16-bit ripple adder, right? So 15 into TC plus max of TCTS. Now what is the data? TC means the delay required for carry. The delay required for carry. The carry propagation delay is 12. So this is 12 plus max of 12, or what is the sum? The sum propagation delay is 15. So maximum of 12 and 15 is 15. So this is 180 plus 15. Your answer is 195 nanoseconds. Your answer is 195 nanoseconds. In the nanoseconds is a NAT type question. Answer is 195. Answer is 195. Right. The timing is divided subject-wise, Pragyan. So you can just aptitude part at least I know, because I am only going to take the aptitude. Aptitude solutions will be 5 p.m. Okay, for aptitude all branch common, the solution will be 5 p.m. That is what I am going to take, and I will be taking some subjects of ECE also, not civil, Pragyan. But yeah, aptitude for all branch common I am going to take. 5 p.m. will be the aptitude solution of Mega Mock Challenge tomorrow only. Tomorrow 5 p.m. Okay, tomorrow 5 p.m. Baki rest of the subjects branch wise and subject wise schedule has been made, and it is there on the app. You can just check it up. Okay. Right. Okay. Now, some basics of the decoder. We all know that decoder is going to take n input and going to produce the corresponding 2 raised to the power n minterms. We call them as 2 raised to the power n output line. Okay, and it is decoder. We also call it as a structure producing coded output from the coded inputs. Here generally our coded inputs here is the n binary variables, and the coded outputs are their corresponding minterms, because minterm is just one of the way of coding the binary variables. Minterms, maxterm, there are different codes. Okay, the outputs of the decoders are minterms of the input variable. Okay, so these are the n inputs, and this is going to what is produced the 2 power n outputs. Let's say for example 2 cross 4 decoder. If I have to look at 2 cross 4 decoder, A and B are the 2 inputs, and there will be 4 minterms generated. D0, which is just like M0, D1 is M1, D2 is minterm M2, D3 is minterm M3. Now what are those minterms? Right, what are those minterms? D0 is corresponding to, okay, I'll show you the table first. D0, it is corresponding to 0, 0. So there are 2 bits, it will have 4 combinations, 0, 0, 0, 1, 1, 0 and 1, 1. And we all know how to convert this truth table into a code. That code was minterm, that we learned in the last class. One is minterm, one is max term, one is SOP, one is POS. Okay. So if it is 0, 0, if it is 0, 0, what is the minterm? What is the minterm? It is A bar, B bar, right? It is A bar, B bar. So the decoder output D0 corresponds to the minterm M0, and that is nothing but 0, 0 combination, which is A bar, B bar. D1 is equal to M1, that is 0, 1, A bar, B. D2 is the minterm M2, that is 1, 0, A, B bar. And D3 is the minterm M3, and that is AB. That is AB. Right. That is AB. As in, Nishu, please specify the point little clearly. Okay, this is what is the logic structure. Very easy. It is just AND gates and inverters required. AND gates and inverters required. This is the logic diagram. Like this is D3, AB. You know, inverters are also available. So A bar, B bar fed into this first gate produces the D0 and etc. Okay. Abhishek, exactly can you specify? This is a revision session. This is not a basic session. Okay. Now, similarly, you can have a 3 cross 8 decoder, which will take the 3 binary variables as the input and produces the 8 decoder outputs D0 to D7, like the minterms M0 to the M7. And this is what the truth table will look like. No need to discuss this again. We all know 0, 0, 0 means D0. 0, 0, 1 means D1. Suppose it is 1, 0, 1, 0, 1 is 5. So D5 will be raised high. 1, 1, 1, 1, 1, 1 is 7. So this is going to be the turn for D7 output. Okay, and again, if you want to draw the logic circuit, it is going to be AND gate, 3 input AND gates, and basic inverters. Basic inverters. The decoders are also available with the enable pin, and there may be decoders with active high enable pin or active low enable pin. What is the concept of this enable pin here? What is the concept of this enable pin here? If I look into this truth table, let's go back to the 2 cross 4 decoder only. Let's go back to the 2 cross 4 decoder only. If this is the 2 cross 4 decoder, if this is the 2 cross 4 decoder, suppose the user is not active on the circuit. Suppose the user hasn't applied any input. Let's say the inputs were previously at 0, 0 only. User has not applied any input. Let's say because user has not applied any input, so both the inputs are suppose 0, 0 in this particular logic. But if both the inputs are 0, 0, still the decoder output is high. Somebody is not using the circuit. There is no user using the circuit, but still one of the output is high. Circuit is producing the output. Circuit is unnecessarily active. So we have to include a functionality to make the circuit active or inactive, to make the circuit enabled or disabled. So that is why we include a enable pin in the decoder. That is why we include an enable pin in the decoder. Okay, and there are two types of decoder, two types of enable pin, as I told you, active high and active low. What is the active high? इसको देखते हैं पहले. What is the active high enable pin functionality? It suggests that whenever the enable pin is high, look into this, whenever the enable pin is 1, the decoder will work as it is. As it is means 0 0 D0, 0 1 D1, 1 0 D2, 1 1 minterm D3, isn't it? But if the enable pin is 0, whatever may be available at the input line, whatever may be the value of A and B, all the decoder outputs, look into this, all the decoder outputs are going to be low. All the decoder outputs are going to be low. That's it. Okay. All the decoder outputs are going to be low. Okay. So that means the circuit is not enabled. So this circuit is enabled. This circuit is enabled when the enable pin is equal to 1. This circuit is enabled when the enable pin is equal to 1. Acha. This is the logic diagram of a decoder with enable pin. Okay. This is the E functionality shown here. Right. Acha. How to change the logic diagram then? How to change the logic diagram? There is a very small correction in the logic diagram. I'll show you there with the previous case only. What is the change in the logic diagram? Have a look into this. Have a look into this circuit diagram. The circuit should produce the decoder outputs only when the enable pin is high. What we can do is, इसको चलो copy करते हैं. Let's not change it here. Let me just copy this slide and let me duplicate this slide. Just a moment. Have a look into this. We want to study the decoder with the enable pin and how to change the circuit diagram. The circuit should be enabled only when the enable pin is 1, and if the enable is 0, all decoder output should be 0. That is what I want, na? So isko dekhenge aap. Just understand this. What we are only going to do is take the enable pin and make it as the input, one of the input to all the AND gates. Make it as input, one of the input to all the AND gates. Ab dekho, if the enable is 0, suppose, if any of the input to AND gate is 0, output will always be 0. If enable is 0, all 4 AND gates receive 0, 0, 0, and the output of all the AND gates will be 0. All decoder outputs are disabled. All decoder outputs are disabled. Correct. But if the enable is 1, then what is this output? Then this reaches 1. This is AB, so this is AB. This is the regular. This will be produced high when both A and B are 1. Right. This will come high when A is 1, B is 0. So decoder will work as it is. Okay. So you just have to include this enable functionality. Okay. You have to just add this enable functionality with all the minterms that were generated. Okay. Similarly, guys, there is a decoder with active low enable pin. There is a decoder with active low enable pin. Active low suggests that the decoder is going to perform when the enable is low. Low means 0. The decoder is going to perform and produce the output when enable is 0. But if the enable is 1, whatever may be the input, X's don't care. If the enable is 1, whatever may be the don't care, all 4 decoder outputs must be 0. All the 4 decoder outputs must be 0. All the 4 decoder outputs must be 0. Okay, that is the circuit is disabled. Okay, this is the logic representation of the circuit with active low enable pin. It is commonly represented, see, it is represented either with a bubble, or it is also represented sometimes by just placing the bar on E. This is also the possible logic representation, E bar, placing a bar on E, right? Or sometimes they do both. All of these are the representation of active low enable pin. All of this is the representation of active low enable pin. So you have to read from the given question that whether the pin is active high or active low. Okay. Acha, what should be the circuit diagram corresponding to it? What should be the circuit diagram corresponding to it? Only thing is, if I go back to the previous, rather than E, you have to apply the E bar here. How do you produce E bar? Take the E and invert it. Okay. So you have to feed E bar rather than E. Okay, you will get the active low circuit diagram. Chalo. One small question here. So one more formula coming up from decoder. What is the number of 2x4 decoders required to implement a 4x16 decoder? What is the number of 2x4 decoders required to implement a 4x16 decoder? Now, what is the formula and what is the technique to solve these questions? What is the technique to solve these questions? Come on, let's check. What is the formula and what is the technique to solve these questions? How many 2x4 decoders are required to implement a 4x16? So I'll tell you the formula in general, because this is also an important area from the decoders. Okay, so theory is huge, but the one which we can formulate, the one which is important for gate, that is what we are tracking about. Okay, if you want to implement the m cross 2 power m decoder using a n cross 2 power n decoder, step number 1, divide the number of required outputs 2 power m by the given output in a decoder. What is the type of decoder given to you? N cross 2 power n decoder is given to you. इसको मैं ऐसे लिख देता हूं. N cross 2 power n decoder is given to you. You have to design what? You have to design m cross 2 power m decoder. Okay, so the decoder that you have to design, what is the number of output lines? 2 power m. What is the number of output lines in the given decoder? 2 power n. Divide both. 2 power m upon 2 power n. Okay. Suppose you get n1. Divide again. Suppose whatever the result you obtain n1, divide by 2 power n. Further divide by 2 power n. Okay. अब इसको भी मैं और सिंपल तरीके से बताता हूं. Let's start doing here. Okay. So I divide how much? 16 divided by 4. Okay. Answer is 4. Right. Now I take 4 by 4. How much is the answer? How much is the answer? So 16 by 4 was equal to 5. Wait, 4 by 4, sorry. 16 by 4 answer is equal to 4. 4 by 4, the answer is equal to 1. Okay. Now, again I will divide. Every time, whatever answer you get, divide by 4. Divide by the number of outputs in the given decoder. Okay. Then continue the steps until the answer comes either 1 or a fraction, which is not an integer. Okay, if it is a fraction, take its greatest integer function, and the total number of decoders required are n1 plus n2 plus n3 etc etc etc. इसको थोड़ा simple terms में लिखते हैं. This may be confusing to the students. देखो 1 by 4. Okay, what is 16 by 4? Is 4. What is 4 by 4? That is simply 1. What is 1 by 4? What is the 1 by 4? Yes, greatest integer means the GIF function, that is known as the floor functions. I'll make it little simple for you. Okay, 1 by 4. 1 by 4 is 0.25. 0.25 ka floor is 0. Whenever the answer turns out to be 0, stop. Answer turns out to be 0. Please stop. Okay, what is your total answer? The total answer is 4 plus 1 plus 0, and that is equal to 5. Sir, what is this floor function? इसको मैं separately लिख देता हूँ आपके लिए. What is this floor function? I call this bracket usually as the representation of floor function or the greatest integer value that they were mentioning. GIF, greatest integer function, right? It is the integer. It is the integer which is just below that number. Floor, what is the meaning of floor? Why do I call it as floor? Because it is easy to remember. Floor, just below you. Ceiling is just above you, right? So when I am writing 0.25 now, if I see in the number line, 0.25 is between 0 to 1. So what is the floor value of this? What is the floor value? Uske niche kya hai? Bottom. What is there on the bottom side? That is 0. Suppose if I ask you, there is a number 3.89. What is the floor corresponding to it? So what is the integer below 3.89? Okay. What is the integer below 3.89? That is 3. That is 3. Okay. Okay, so whenever the answer turns to be 0, you have to stop. This is the procedure. Okay, if you have understood the procedure, one more. How many 2x4 decoders are required for 5x32? Same procedure, sir. Same procedure. 32 divided by 4. Number of outputs in the required decoder divided by number of outputs in the given decoder. 32 by 4, 8. This is the integral part, no part, right? What is the floor of integer? It is same. 8 by 4, that is 2, right? 2 by 4, 0.5. What is the floor value of 0.5? It is 0. So my answer, 0 पे stop करेंगे. So my final answer is addition of all of them. My answer is 10 this time. My answer is 10 this time. My answer is equal to 10 this time. Okay. Correct. All made the correction? Yes. Chalo. Next one. How many 3 to 8 line decoders with an enable input are needed to construct a 6 to 64? Okay, so again simple. 64 by 8, this is 8. 8 by 8, this is nothing but 1. 1 by 8, it is 0.01, 0.125. The floor of that is 0. Once you get the 0, stop. Once you get the 0, that is stop. The answer is 9. 8 plus 1 plus 0. Answer is equal to 9. 8 plus 1 plus 0. Correct. The answer is equal to 9. Chalo, this one is simple. Yes, Nishu, 10 only. No? Just recheck that value again. Okay, the answer is equal to 9. Simple. So this is a technique. In a sense, this is the next technique. Let's go to the next one. Okay, now from the decoders, what else you can expect is like logic realization. First, let me give you an example. Can you implement a full adder? Now, decoder can help you to realize any logic, because any logic function you can express in the canonical forms. Canonical forms include what? Minterms and the max terms, right? For example, full adder, right? So, what was the full adder? Full adder constitutes two outputs, sum. Sum in the canonical form is summation 1, 2, 4, 7. So, to implement the sum output, what do you need? To implement the sum output, what do you need? You need the minterms 1, 2, 4, 7. If you take a decoder, it contains all the minterms M0 to M7. Yeah, it contains all the minterms D0 to D7. Whatever minterms you need, you have to just do the summation. That is logical OR. M1 plus M2 plus M4 plus M7. So, you have this D1 plus D2 plus D4 plus D7. You have to take them and feed it into a 4-input OR gate. This realizes your sum. Okay. Similarly, what was the carry output? Carry output was given by summation of the minterms 3 and 5 and 6 and 7. 3 and 5 and 6 and 7. No idea, Abhishek, right now. That is decided by the YouTube team. I can't say. Okay. So now you have to add 3, 5, 6, 7. So all the minterms are available. All minterms of 3 variable. Full adder has 3 inputs, na? Full adder has 3 inputs. So all minterms, all possible minterms of 3 inputs are available at the output of decoder. You have to just know what is the logic functionality you have to realize and put it here. Okay, so I need here now 3, 5, 6, 7 fed into another OR gate. It produces the output C out. Right? It produces the output C out. Correct? Okay, now as far as gate exam is concerned, because we are revising for gate right now, rather than logic realization, logic implementation, they will give you a decoder, which has used some particular minterms, and they are asking what is the final output. Okay, this is what is the next. So see, some portion in the digital we can only revise through question, because it is a category of question. Decoder is very simple topic we have studied. Very basically only you have to go through decoder. It is not very important topic, but yeah, this is the type of expected question. Formula, it has to go back to KMAC. There is no special formula for this. So that is why I am showing you in the revision, I am showing you the category of the question. Hi, lovely, no problem. If you are new, you can also join and continue watching the session. So what you have to do in this question, what you have to learn in this question, you have to just read, what is this F? What are the minterms? OR gate, matlab it is providing the summation. Summation of what? Look into this. D0, then you have D2, then you have D3, then 6 and 7. So it is summation of the minterm 0, 2, 3, 6 and 7. Okay. Output by default means the standard output, minimized output, reduced output. So for that I will use the K-map. Just.
the 3 variable K map will be used and the answer will be simplified. That's it. इतना ही करना है. My 3 variables are A, B, C and the minterms that are generated are 0, 2, 3, 6, 7. 0, 2, 3, 6, 7. All about the minterms we have, all about the K maps and the minterms we have seen in the last class. Okay, now this is clearly a quad coming up, and is this single? No, the first and last columns are adjacent, so this can also be paired with the adjacent one. Okay, now regions, this is A, last 2 columns B, center 2 columns C, right? This is the quad which is belonging totally to B. So what is the naming of this quad? This quad belongs to B. What is the name for this pair? Dekho, this is above A, that is outside A. B, 50% in, 50% out. There is no 50-50% rule, either in or out. Okay, so B nahi aayega. C, this portion is C, so it is totally outside C. It is totally outside C, so it is C bar. It is totally outside C, that is C bar. Okay, so what is the answer? What is the Boolean function f? Then it is containing a term B, then it is containing another term A bar, C bar. So B plus A bar, C bar. Correct? Yes, Nishu. Okay, so this is the canonical expression. But output, even if not specified, output by default means the standard output, reduced output, minimized output. This is the canonical form of the function, and that one is the standard form or minimized form of the function, B plus A bar, C bar. So that is what. There is no formula here. This is a technique of K-map which I have revised you in the last class. But this is a type of question I want to revise. So I am showing you in the form of question. Okay, I cannot show any formula for this. Okay, next. Okay, similarly, what are the types of questions expected from multiplexer? Because in multiplexer also, if I talk about the gate level of question, you are not going to much expect any formula type of approach, but question type of approach. So what is that type of approach? Let us discuss about that. Okay, so we all know that multiplexer, it is going to select one of the multiple inputs and connect it to the output line, transmits one out of the multiple inputs. What is that one out of the multiple input line? That depends on the value of select line. So a multiplexer has 2 power n input line, right? To select 2 power n variables, how many bits are needed? N bits are needed. So we have n select lines and 1 output line. This is also known as a 2 power n cross 1 mux. Right, it multiplexes 2 power n signals into one single channel using the n select lines. So the select lines are also known as the control lines. Yes, the data selector issue. Okay, so if I take an example of, let me make you understand, 2 cross 1 mux. Okay, so there are 2 input lines, I0 and I1. Okay, the information available on the 2, one of the information has to be connected to the output. It has to be passed. But which input? Which information, I0 or I1? That will be decided by the select line. That will be decided by the select line, that is known as S0. That is primarily known as S0. So simple logic, if S0 is 0, I will pass the information I0. If the S0 is equal to 1, I will pass the information I1. This is what is a 2 cross 1 mux. Now can you put it into a logic functionality? Very simple. So what is the logic expression for this f? Dekho, if the select line S0 is 0, 0 means if a variable is 0, how do you code its minterm? If A is 0, we write A bar. So S0 is 0, so S0 bar, and when S0 is 0, I will pass I0. Plus, if the S0 is 1, 1 means you will only write S0, multiply by I1. Now see the logic. Suppose S0 ko 0 kiya. If you plate S0 is 0, this term is gone. 0 complement is 1. F is equal to how much? I0. F is equal to I0. So output receives the input I0. Output receives the input I0 if the select line is 0. Suppose if the select line is 1, right? 1 complement is 0. This is gone. This is 1. So output is 1 into I1. That is I1. What is the output? The output receives the information from I1 if the select line was equal to 1. So this logic functionality justifies our task, our truth table. It simply justifies our truth table and our task. ठीक है ना? बहुत बढ़िया. चलो, all cool. This is done. This is clearly satisfied. This is simple. Moving ahead to the next. Okay, this is the logic. Sorry, where is that? This is the logic diagram. Same thing I explained you. This is S0 bar I0. This is S0 I1. Then we need to do the addition of that. For that, a logical OR gate is there. So this is what is a 2 cross 1 mux internal circuit diagram. Okay. Acha. Now if I want to take a 4 cross 1 mux. Now if I want to take a 4 cross 1 mux. Okay. The same thing. Now 4 cross 1 mix means I have 4 information, and 1 out of the 4 information has to be passed through this channel connected to the output. What is that information? So to select, to control 4 quantities, how many control or select lines are needed? 2, because 2 bits can make 4 combinations. 2 bits can make 4 combinations. So here there will be 2 select lines. Here there will be 2 select lines. Right. On the value of select line, suppose 0, 0, I will have I0. 0, 1, I will have I1, and etc, etc, etc. So what is the Boolean function for such a multiplexer? What is the Boolean function for such a multiplexer? 0, 0 means S1 bar, S0 bar. 0, 0 means bar. Okay. And multiply by I0. So that when 0, 0 comes, this becomes 1, 1. F is 1, 1 I0. That is F is equal to I0. Acha. Plus 0, 1. S1 bar, S0 I1. Plus S1 S0 bar I2 1 0 plus S1 S0 I3. This is what is the Boolean functionality of 4 cross 1 mux. You don't have to remember this. You don't have to mug up. You just have to remember what a 4 cross 1 mux will do, and by this truth table you will be able to easily write down. Not even draw the truth table every time. By the logic, 4 cross 1 mux, 0 0 I0. So S1 bar S0 bar I0, 0 1 S1 bar S0 I1, and etc, etc, etc. You can write down instantly if required. Okay. Right. Similarly, you have a 8 cross 1 mux. Just go through the truth table. It is self-explanatory, nothing more. I have just written the 8 cross 1 mux logic diagram and the truth table. Okay. To select 8 inputs, I need 3 select lines. So here there are 3 select lines. 3 select line, all 8 combinations, and the corresponding output is shown here. Okay. Now, logic realization using the multiplexer. Acha. Sometimes rather than the numerical question, these factual and concepts are also important in some competitive exam, right? Now a multiplexer has n input lines and it has n select lines. It has n select lines. If it is a 2 cross n power 1 mux, it has n select lines. And how many input lines? 2 power n input lines. Okay. If you connect n variables to the n select lines, if you connect n variables to the n select lines, yes, Abhishek, please ask me. You are able to realize a function of n variables. But what will go to the input lines? Input lines can be either 0 or 1, ground or VCC, high voltage or ground. But suppose you connect n variables to the n select lines, and also you connect a variable either in true form or complemented form, means A or A bar. You connect one variable at the input lines. That means at the input lines you may require an inverter as well. Okay. So if you allow one inverter in addition, connect the n variables at the n select lines, connect one more variable at the input lines for which you may need inverter as well, then you will be able to realize a function of n plus 1 variables. How to realize? What is the method? वो भी बताएंगे. If you want to realize a function of more than n plus 1 variables using a 2 power n cross 1 mux. 2 power n cross 1 mux means n select lines. So using n select lines, you want to realize a function of more than n plus 1 variables. So you will have to use extra logic circuitry at the input lines. This can be implemented by using extra gates at the input side, at the input lines side. Okay. Now, how to actually implement this, let us understand. But these are some points important to be remembered. Sometimes they can diss this. Okay. Chalo, next. Implement the Boolean function. Okay. So there is a 4 cross 1 mux. There is a 4 cross 1 mux. Okay. Now, 4 cross 1 mux mein, dekho, understand this once again. 4 cross 1. It has how many select lines? 4 is 2 power 2. To select 4 inputs, 2 select lines are needed. So 4 cross 1 mux will have 2 select lines. Right. But the function that is given to you, 2, 3, 5, 7, that is a function of 3 variables actually. Up to 7 minterm it is going, na? Up to 7 minterms it is going. 2, 3, 5, 7. 2, 3, 5, 7. So we have to realize a 3 variable function using a 4 cross 1 mux. 4 cross 1 mux has only 2 select lines. Okay. So 3 variables are there. 2 out of the 3, 2 variables out of these 3 will go to the 2 select lines. 2 variables out of these 3 will go to the 2 select lines. What about the third variable, dear? What about the third variable, dear? Thank you, Pawan. What about the third variable? It has to be connected on the input lines. It may be connected in the true form or complemented form, but it has to be connected at the input side. Okay, chalo. Once again, guys, we know that we don't have time for derivation in this session, so I will tell you the technique. The technique is implementation table. The technique is the implementation table. Achha, 2 out of the 3 variables are there at the select lines. What are the 2? I select BC. Suppose you may select AB, but our answers will mismatch. Na? That is why I am specifying. Let us select BC at the select line. So A will be at the data line. What happens to A? A will be at the input lines. Right. A, when I say A, or it could be A bar. So I need an inverter as well. But understand the method. The method is implementation table. The method, again I'll tell you here, there is no formula, but there is a technique. What happened to the board? The technique is implementation table. It is eating some words. The technique is implementation table. Hello, Bruce. Right. Current COA, entire revision in one session. Not only formula, because for COA students are looking not only formula but some theory and concepts also. For COA we are planning to bring another session. Okay. Chalo. Implementation table की बात करेंगे. What is that implementation table? So understand here. We have 4 input lines. I0, I1, I2, I3. We have 4 input lines. Okay. What should go at the input lines? What should go at the input lines? It is either A or A bar. Make 2 rows. One is for A bar, one is for A. What are the minterms to be written here? What are the minterms to be written here? Now everybody, you all know the binary combinations of ABC. This board is troubling me. Let me write down here. Let us see whether it is that slide problem. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. Okay. Now, we know all the binary combinations of ABC, everybody. What are the minterms at which A is low? See, in a Boolean function, when do you write A bar? When A is 0. In a Boolean function, when do you write A? When A is equal to 1. Right? So guys, look into this and tell me, look into this table and tell me what are the minterms in which A is low? The first 4 minterms, that is 0, 1, 2, 3 if I talk in decimal. And what are the minterms in which A is high? That is the next 4 minterms, 4, 5, 6, 7. Isko remove karte hai. Right, so what are the minterms I am going to write here? I am going to write 0, 1, 2, 3. Here I am going to write 4, 5, 6, 7. ठीक है जी? Now this is the implementation table ready. Now let us talk about the function. What is the function you are going to implement? 2, 3, 5, 7. F is the function, summation of the minterms 2, 3, 5, 7. 2, 3, 5, 7. Next is, circle these minterms, bubble these minterms. So 2 and 3 and 5 and 7. Okay, now what is the method, right? What is the method? Look, first column, is there any minterm included? No. So it is 0. Second column, you see, what is the minterm included? 5, and that is coming in the row of A. So here you have to write down A. Look at the third column. The minterm is corresponding to A bar. Write down A bar. Look at the last column. The minterm is corresponding to both. There is a minterm of A bar, there is a minterm of A. Guys, what is the value of A bar plus A? In Boolean, A bar plus A is equal to 1. So when both circle, write down 1. So simple logic is, when nothing is circled, write down 0. When both are circled, write down the 1. Right? Bottom one circled, A. Above one circled, A bar. That is the implementation table. That is the implementation table. Right? So this is the I0, I1, I2, I3. Right? I0, I1, I2, I3. If I have to show you the answer, ye raha answer. So there is a 4x1 mux. What you have collected at the select lines पे connect किया BC. What to connect at the input lines I0, I1, I2, I3, that I have calculated for you. I0, I1, I2, I3, what to connect, that I have calculated for you. Okay, let me write down that calculated result. 0A, A bar and 1, and this is the function F. 0A, A bar 1, and this is the function A. 0A, A bar 1, and this is the function. This is the answer. This is the logic realization using the mux. But sir, see, that is what this particular topic doesn't have the formula. It has a technique. So I'm explaining you the technique. Ab dekho, B and C should be at the select lines. But suppose somebody says that, sir, why BC? I want to apply AB or AC at the select lines. So next, let me tell you the next possibility also. Right? Implement a function now. Function ko thoda change kiya hai, 1, 3, 4, 6. Again using a 4x1 mux with A and B at the select lines. If A and B are at the select line, so what is there at the input line? C will be there at the data lines. C will be there at the input lines. Again, when I say C, it automatically means C or C bar, true or complemented form. So here, what is there at the input line? What should be the implementation table now? Will you follow the same implementation table? That is the mistake done by most of the aspirants. They will copy the same implementation table. But I have explained you what is the logic of the implementation table. Accordingly, you have to make implementation table. देखो ये fix है. Write down I0, I1, I2, I3. Write down the I0, I1, I2 and I3. ठीक है. Write down two rows here. One is C bar, one is C. One is C bar, one is C. Now, what should be the minterms coming in the C? Those minterms at which C is high. Those minterms at which C is high. Those minterms at which C is high. अब ये देखोगे आप. C is high at odd minterms. Alternately odd minterms. At the alternate minterms. 1, 3, 5, 7. 1, 3, 5, 7. तो वही तो लिखेंगे ना यहाँ पे. Right. 1, 3, 5, 7. So remaining 0, 2, 4, 6 at the top. So see, implementation table changed. Logic behind that is same. Implementation table change. Many students I know will copy the same implementation table 0, 1, 2, 3, 4, 5, 6, 7. They'll give the wrong answer. Right. So what is the answer then? Okay. What is the answer then? Chalo bubble karte jayenge. Ab, right. What is the function in the question? The function is summation of the minterms 1, 3, 4, 6. 1, 3, 4, 6. तो ये कितना हुआ? 1, 3, 4, 6. I have bubbled. Right. Okay, only C. This is also only C. This is C bar. This is C bar. Your answer is ready. C, C, C bar, C bar. C, C, C bar, C bar. C and C and C bar, C bar. That is the answer. That is the answer for the question. This is how this multiplexer will implement the Boolean function summation of the minterms 1, 3, 4, 6. Okay. I hope this technique is there. What is the next type of formula? Again, I repeat, there is no formula. But there are techniques and questions. So what is the next type of question from the mux? Some mux circuit is given. Some mux circuit is given. Yeah. A and B, A being the MSB. Okay, A and B जिस sequence में बोला है ना, normally how do you write down a number from MSB to LSB? So they have told select lines is AB. So of course I will treat A as the MSB, right? Although they can specify also, but if they have not specified, so how do you read any variable or any expression from MSB to LSB? So we'll treat accordingly. ठीक है निशु? Yes. What is the output of the following circuit? Okay, so it is again not a formula. It is a law. It's a question that you can solve here very simply. What is the output? This is a 2 cross 1 mux. You know how to solve 2 cross 1 mux? X bar, select line 0. That is X bar. With that you have to select Y, I naught. This is like I naught. Okay. First, if the select line is 1, right, you have to select the next input. That is the I1 and that is 0. Okay. What was the function? S naught bar I naught, S naught के साथ I1. Okay, so this is nothing. This is X bar Y. Okay. Okay. So what comes here? Let's suppose this is some variable Z. So this will, actually Z is already written here. I'm sorry. Okay. Let's say this is some variable P. So this will be P bar. So what is Z now? See, what is Z? What is the output? Sorry. Suppose output is F. So select line 0, Z bar. With Z bar I naught. What is there at the I naught? P. Select line 1, that is Z. With that select line I1, input line I1, that is equal to P bar. So your answer is Z bar P plus Z P bar. Okay, we have to simplify this little bit now. Okay, so your output is equal to Z bar. This board is creating some problem. Z bar into P. ये देखो. Unnecessary, that board is creating problem for me. Okay, Z bar into P. P बोले तो X bar Y plus Z into P bar, X bar Y whole bar. So we have to just simplify this. The first expression is X bar Y Z bar in sequencify, right? Second, X bar Y का whole complement will become X plus Y bar. So X into Z. Next आ जाएगा plus Y bar. तो Y bar into Z. So X bar Y Z bar plus XZ plus Y bar Z. This is the answer. This is the answer. X bar Y Z bar plus XZ plus Y bar Z. That should be the answer to the question. Right, dear? That is the answer to the question. So this is how the category of question also you can expect. Manisha, please say the doubt exactly. Repeat means I'll repeat the very same thing. So if you say the doubt, I can, try to handle it in a better way. Yes. The Boolean function realized by the logic circuit shown. What is the Boolean function realized by the logic function shown here? Boolean function realized by the logic function shown here. Okay. So again, it's a 4 cross 1 mux with this is C and D. Okay, this is missing. This is C, this is D. This is C, this is D. Okay, so we have to just write down in the minterm form A bar B bar. Select line 0 0 means A bar B bar. With the A bar B bar, I naught will come, that is equal to C. Next is A bar B 0 1. 0 1 pe I1 will come, that is equal to D. Next is 1 0, that is A B bar. A B bar I2 will come and I2 is equal to कितना आएगा यहाँ पे? This is C bar. C bar. Next is 1 1. With 1 1 I3 will come, and what is I3? What is I3? It is the AND gate preceded with bubbles, right? So C bar into D bar. It's just like a NOR gate. It's just like a NOR gate. तो यहाँ पे आ जाएगा C bar D bar. 1 1 0 0. This is already a minterm. अब देखो यहाँ पे क्या क्या combinations बनेगा. Right? I've told you how to create the minterms in the last class. Let us repeat that. A bar B bar C. This is like 0 0 1, but D is missing. A bar B D 0 1, C is missing, D is 1 again. A B bar C bar 0 0, D is again missing. This is 1 1 0 0. ये तो minterm clear हो गया, right? 0 0 1, D is missing ना, तो this is 0 0 1 0, right? 0 0 1 1, right? यहाँ पे अगर देखें 0 1 0 1 0 1 1 1. 1 0 0, whatever is the missing, that is X. It can be either 0 or 1. So 1 0 0, again a 0, or 1 0 0 or a 1. That is 1 1 0 0. अब इसमें से कुछ repeat हुआ क्या? right? So no, nothing is repeated. So what is the answer? Dekho, 2, 3, 5, 7, 8, 9, 12. Where is that? 2, 3, 5, 7, 9. 2, 3, 5, 7, 8, 9, 12. Answer is D. Answer is D. Got this, everybody? If you're getting it, do not forget to like the session. So this is like 2, 0, 0, 1, 1, 3, 5, then 0, 1, 1, 7, 1, 0, 0, 8, 1, 0, 0, 1, 8, decimal 9, 1, 1, 0, 0 is 12. So answer is D. Correct? Answer is D. Correct, na? The answer is D. Answer is equal to D. Okay, you can take a similar question. I just wanted to show you the pattern. So kindly take this question as the homework. Kindly take one question as homework, because we are not focusing on question practice here. We are focusing on revision of formula, revision of techniques, whatever depends on the topic. Okay, next question. What are the minimum number of 2x1 mux required to generate a 2-input AND gate and a 2-input XOR gate? AND gate कैसे बनाएंगे? Very simple. Very simple. How many? What is the type of multiplexer given to you? 2x1 mux. Right. You are given 2x1 mux. Okay. Let us understand the implementation of AND gate through it. This part is simple. 2x1 mux has only 2 input lines. And because of only 2 input lines, it has only one select line S0. Okay. What I will do is, I read the AND gate. Now, what is the AND gate? A into B. So यहाँ पे apply किया A. Select line I apply A. Right. Select line I apply A. Right. The output here is select line, that is S0 bar I0 plus select line 1, that is S0 with I1. S0 bar means A bar, but I don't want A bar. So I0 should be 0 plus S0 A. I want A B. So I1 should be B. I1 should be B and this should be 0. I0 should be 0. Right. So you are able to do it using only one multiplexer. You are able to do it using only one multiplexer. That is clear. We are able to do it using one multiplexer. Na? That is simple. Okay. Now I need to implement the XOR gate also. I need to implement the XOR gate also. So चलो XOR gate को भी देख लेते हैं. I need to implement an XOR gate also, right? Using the same 2x1 mux. S0, I0 and I1. Okay. Now, I need a XOR gate. ध्यान देना. What is the output of XOR gate? Output of XOR gate. यहाँ पे देखो क्या आएगा. Here it will be S0 bar into I0 plus S0 into I1. But I need A bar B plus A B bar. There is complement in both. A bar B plus A B bar. There is complement in both. No problem. Let us apply the select line as again A. Let us apply the select line as again as A. Right. So this becomes A bar. With A bar I want B. So I0 becomes B. I0 becomes B. Plus S0. S0 को A fix किया. But I1 should be B bar. I1 should be B bar. See, this A bar is automatically included within the multiplexer. But now I need external B bar. And what is the question asking you? What is the minimum number of mux required? They are not allowing anything else. See, that is a confusion. Many students will give the answer here as 1 and 1. Okay, because you will apply B bar and you will feel that 1 mux sufficient. But dear, where is the B bar? Where is the B bar? That is not available for you right now. That is not available to you right now. So you have to design this B bar also. You have to design the B bar. To design the B bar, I will use one more multiplexer, right? Where I will again, in this multiplexer, ध्यान देना, in this multiplexer, I will feed B, right? I want B bar, right? I want B bar. Right, so देखो, what is this multiplexer going to do? ध्यान देना. Select line 0, S0 bar into I0. So B bar into 1. Right. I only want B bar into 1. That's it. Otherwise, what it will do? B into I1 भी करेगा ना ये. right? So I don't want B into anything, so this should be 0. So I naught should be 0. So this is an inverter. So inverter also has to be implemented using a multiplexer. So what is the answer? 2 multiplexers. Yeah, Ramesh, but how do you design the inverter? That is designed again using multiplexer, because question में क्या बोला है? You only and only have the multiplexer, right? So the correct answer, the correct choice for the question is option number A, 1 and 2. It's not 1 and 1. Okay, many students misunderstand this question. That is why I discussed this. Okay, that is why I discussed this. It is 1 and 2. Okay, so this is logic. Yeah, any simple gate implementation. Okay, yeah, one more basic formula that can, become in the form of formula or as well as in the form of code converter, binary to gray code converter. Binary to gray code converter. Actually, what is the formula for any, gray code, right? The bit I of the gray code is given by, as you are able to see also, it is simply given by Bi XOR Bi plus 1. G0 is XOR of B0, B1. G1 is XOR of B1, B2. G2 is the XOR of B2, B3. Right? This is also the formula for conversion from binary to gray code. Binary to gray code. Reverse. Gray to binary. Gray to binary. Gray to binary. Okay. So here B3, this depends on G3. But look at the B2. MSBs of both the codes are always same. You know that from the number system. But what is the B2? B2 is the XOR of G3 and G2. What about B1? B1, it is the XOR of G1 with the previous XOR. It is G1 XOR of the previous G2 XOR G3. And similarly, you will have B0 as well. Okay. So what does this imply? What does this imply? I want to convert gray to binary. I want any binary information. I can write down Bi should be equal to how much? Suppose B3, it is only G3. But B2, G3 with G2. B1, G1, G2, G3. तो ऐसा करेंगे, Bi is Gi XOR with higher Gi plus 1, XOR with Gi plus 2, etc., 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 up to the MSB. Right? Up to the whatever is the MSB bit of G, depending on the number of bits. Let's say the number of bits is n. Number of bits n hai, so this will be Gn minus 1. It is the XOR of all the gray bits from the I up to the MSB. Right. Same thing is applicable here also. B0, it is the XOR of, see how much? G0. Then, ऊपर से क्या आया? G1, G2, G3. G1, G2, G3, isn't it? Isn't it? Chalo. That's it, guys. Now, yes, let us talk about this case first of all. Okay, let us also quickly revise some important fundamentals about the latches, flip-flops and the counters also. Okay, so that is also an important area you need to revise. SR latch, the very fundamental NOR gate latch. S and R standing for set and reset. A quick revision only. But yeah, especially regarding to the flip-flops and counters, I have taken detailed sessions also. Right? So that also you can watch if you are facing any difficulty here. Regarding to flip-flops, I have taken, and regarding to the counters also, I have taken the detailed classes with questions, with all fundamental theory, derivations, everything. Crystal clear explanation from the basics. Available on the YouTube. You can search flip-flops by my name. You will get that. Okay. But let us first quickly revise. No need to drive. It's a simple NOR gate structure. But what are the results? S and R, set and reset. So if whenever the S is equal to 1, R is equal to 0, S equal to 1 bole to set, the flip-flop is set. S equal to 0, R equal to 1. Which input is high? R for reset. The flip-flop is reset. If both are not applied, if both are 0, the flip-flop as in the previous state. Same state. It does not change the state. If both are applied as 1, this is the invalid state. The user should not apply this input, because once the circuit enters this state, the next state becomes indeterminate, or the next state may be unstable also. Right? So in the SR flip-flop, S and R equal to 1 is not allowed, right? If only S equal to 1, the flip-flop will be set. Set matlab output will be 1. If only R equal to high, R is reset, so the output will be 0. If both are not applied, if both are 0, 0, the flip-flop doesn't change the state. It remains in the previous state, and both equal to 1 is not applied. It is not allowed. You should take care not to apply this input. This is the basic SR latch, the unclocked version. Okay. To make it synchronize with the clock, we use the clocked SR latch. And how do we have this clocked SR latch? Very simple. We use 2 AND gates, okay, to apply this clock input. Simple logic is कि अगर clock 0 हुआ, if the clock pulse is 0, this is the SR input. This is the actual external SR input. Let's say this is S dash and this is R dash. Sorry, dash here may represent complement. So let us take this as S1 R1. So dear, if the clock pulse is 0, output of both the AND gates is 0, and input of both the AND gates is 0. If the input to AND gate is 0, output will be 0. If the input to AND gate is 0, output will be 0 only. Correct. Output will be 0. Right. So what will happen? S1 equal to 0, R1 is equal to 0, right? And if both the SR input to the latch is 0, the latch is not going to change the state, right? So the next state is equal to Q. In the flip-flop world, we call Q as the current value, Q plus as the next value. Okay, thank you, Sri Lakshmi. But if CP is equal to 1, if the clock pulse equal to 1, right, so what comes here? See, clock pulse 1, R into 1, R aya. This is S. S into 1, you will get the S here. So whatever is the actual inputs you apply, it enters the latch. S1 will be equal to S. R1 will be equal to R. Now what is the next state? Depends on what is the value of SR. That means the next state now, the flip-flop is now open, you can say. The latch is now open, and the next state depends on SR inputs. Inputs can now enter the system. Acha, the inputs can enter the system. The inputs here can affect the system. I can say one more thing here, na? Here, the inputs which are S and R can affect the system if clock pulse is equal to 1. If the clock pulse, up to the point the clock pulse is 1, the inputs can affect the system. Up to the time the clock pulse is equal to 1. And if the clock pulse is 0, the inputs cannot enter the system. This is what is known as what type of clocking? This is a level triggered clocking. This is a level triggered circuit. It will respond to level of the clock. What level? It may be 1 or 0. Here we have taken 1. So these devices are known as what? These devices are level triggered. The latch, the clocked latch is the example of level triggered device. The clocked latch is the example of level triggered device. It will respond up to the clock is at level 1. Right? Up to the clock is at a particular level. So this is a level triggered. So clocked SR latch, don't confuse it with flip-flops. It is a normal latch, level triggered latch, you can say. Level triggered latch. Okay. Now what is the characteristic table? What is the next state equation? Very simple, na? Dekho, SR 0, 0. So whatever is the current value remains the same. 0, 1. What is 1? Reset is 1. So output should be 0. 1, 0. What is 1? S is 1. S matlab set. Device should set. What about 1, 1? I told you 1, 1 is the invalid input combination. You should not apply this because of the risk I told you. So if it is not applied, I can say this is a type of input which does not appear. If an input does not appear, what is the output corresponding to it? We don't care about the output. So output here becomes a don't care. Don't care. Right? That is why we write don't care. Ab dekho. Again 0, 0. So output remains same as previous. 1 ka 1 raha. 0, 1. 1 means reset. 1 0, 1 here is for set, so device is set. Again, both inputs 1 1, so this input can never come. User has to take care, so output is don't care. Output is don't care. This is the logic simple. And what is the characteristic equation? This is known as the characteristic table. What is the characteristic equation or the next state equation? What you will do, you will feed this in the K-map, solve using the don't care condition. You get the output as S plus R bar Q. Q plus is equal to S plus R bar Q. Dear, what is the Q plus? It is equal to S plus R bar Q. Q plus is equal to the S plus R bar Q. Corrected here? Q plus is equal to the S plus R bar Q. S plus R bar Q. By the K-map you can solve. We don't have to derive here. We have to just focus on the final formula. Okay, Q is equal to S plus R bar Q. Now clogged D latch. What is the D latch? I have to just make the correction here. D latch is a modification in the SR latch where the S input, now we call it as D. S input we call it as D, and we take the complement of it. Take the complement of it and we apply to the R input. We apply to the R input. So the R input here is D bar. R input here is D bar. This behaves as a D latch, right? D is for data, or it is also for delay. It is also known as a data latch or a delay latch. This is the table. Okay, you can just verify the table. Very simple to observe here. Very simple to observe. इसकी functionality भी मैं यहाँ पे लिख देता हूँ D latch की. D is equal to 0, Q plus is equal to 0. D equal to 1, next state Q plus will be 1. Sir, why? Why? देखो ना. If D is equal to 1, so D complement is already 0. So what is 1? S is equal to 1, R equal to 0 eventually. S1 R0 set. S1 R0 set. तो device को किया set. अच्छा, next condition. So take the D0. D0, so D bar will be 1. So what is 1? R. What is 0? S. Sir, S0 and R is 1. R for reset. So device should reset. Sorry. Device should reset. So Q plus is 0. So that means whatever D value I am taking, dear, if I take 1, I get the output 1. If I get 0, I get the output 0. So what is the next state equation? It is just copying D. Q plus equal to D. Q plus equal to the D. Simple one. Q plus is equal to the D. Please mind that Q plus is simply equal to the D. Okay, so if I want to look at the characteristic table also, Q plus is just following this particular column, the column of D. Okay, so characteristic table is also there for you, characteristic equation also you have written. Okay, and this is the graphic symbol. Okay, see right now because I am discussing clock latch, so see in front of the clock pulse what is drawn? A level of the clock. That means it is level triggered. What is the logic symbol of edge triggered devices? Yeah, also known as flip flop. वो भी मैं explain करूँगा आपको. Next one, the clock JK latch. Now JK latch is again a modification of the SR latch. Okay, what is JK standing for? What is JK standing for? Jack Kilby. It is the name of the two persons who eliminated the problem of, right? Invalid state condition of the SR latch, Jack and Kilby, and hence this latch was named as JK. So what is that modification? I'll show you here only. Okay, so there is one more feedback connection from Q bar, and this goes to the input, and S will be named as J now. R will be named as K on the Kilby, and there is one more feedback connection from Q, and it comes to the top AND gate. This is what is a JK latch. This is what is a JK latch. The operation of the JK latch, this is in the form of characteristic table. First, let me write down the operation. Okay, so J equal to 0, K equal to 0, first condition. Q plus equal to Q, that is the same state condition, right? Next, J is equal to 0, K is equal to 1. K, J, K, SR. How to remember? J, K is SR. Replacement of SR. K is equal to 1 means R is equal to 1. Reset. Q plus will be 0. This is reset. Okay. Number third, 1, 0 combination. J equal to 1, K equal to 0. J has taken the place of S. S is set. S is set. So Q plus को किया 1. This is set. Next fourth. J equal to 1, K equal to 1. Now, in the SR latch, 1, 1 was not allowed. But in the JK it is allowed. Na? That is why I told you Jack and Kilby eliminated the invalid state. How? No derivation we are doing, but the final conclusion. So in the JK latch, again, formula to important. I will write down the formula, but these conclusions are also important. So this session, whether it is formula or conclusion or technique, everything we have to summarize. We have to take the summary of that topic. Okay. So if J and K are both equal to 1, this is not referred to as invalid state here. There is one more type of state that we call it as the toggle state, complement state. Whenever both J and K are 1, 1, the device will be toggled. When both J and K are 1, 1, the device will be toggled. Q plus will be equal to the Q bar, and this is known as the toggle condition. This is known as the toggle state, also known as complement. Toggle or known as complement. Toggle or simply known as complement. Okay, so this is the characteristic table. As per the conditions I have written, the characteristic table had been written. You can note this. And again, the characteristic table will be put in the K map and final function will be calculated, and that is calculated as J Q bar plus K bar Q. The next state Q plus is J Q bar plus K bar Q. That is the characteristic equation of the JK latch. J Q bar plus K bar Q, and this is the simple graphic symbol. Lastly, we have the clock T latch, T standing for toggle, and it is just one modification of the JK latch. It is one modification of the JK latch. Both the JK inputs are shorted. Both the JK inputs are shorted. That is, they are tied together, and we call it as T. Right? This was J, this was K. Now they are common, and that common node is known as the T. So what is going to happen? What is going to happen? A simple analysis. If T is equal to 0, J and K are both 0 because J and K are both equal to T. If both are equal, it is the same state condition. Q plus equal to Q. If both are 0. But sir, if T is equal to 1, so J and K are also 1. And if J and K are 1, what we understood just now? If J and K are 1, this is a toggle condition. So Q plus will be equal to Q bar, that is known as toggle, right? And that is why this device is named as the toggle latch, because whenever T is high, whenever T is applied, it toggles the state. Whatever is the current state is complemented, is toggled. It is toggled. Based on these observation, the characteristic table. So let me write down the characteristic equation and table here. It is missing. Right, so we have Q, we have T. Let me write down the characteristic table for you. Right. अब ध्यान देना. Whenever T is 0, no change of the state. 0 remains 0. 1 remains 1. But if T is 1, then you have to toggle. T is 1, so 0 toggle to 1. T is 1, 1 toggles to 0. Now this is like what? The output is high when both the inputs are different. 0, 1 and 1, 0. This is 2 input XOR. This is just like 2 input XOR of Q and T. This is the XOR of Q and T. This is known as the characteristic equation. This is the characteristic equation, Q XOR T. This is the characteristic equation for T latch, right? Now flip-flops, like we discussed the clocked latches, flip-flops are edge-triggered devices. Okay, no need to go for definition and theory part, but just a quick review in few seconds. Okay, flip-flops are edge-triggered devices. There can be positive edge-triggered device, there can be negative edge-triggered device. Right, this is positive edge-triggered. Acha, what is edge-triggered first of all? What is edge-triggered? A flip-flop, a device which will only respond to the edge of clock. Edge means transition, and there are two types of transitions in general. A transition from 0 to 1 or a transition from 1 to 0. Right. So the flip-flop can respond from the transition from 0 to 1, or it can respond of the transition from 1 to 0. Such a flip-flop will be negative edge-triggered flip-flop. This will be named as negative edge-triggered. Okay. One way of designing this flip-flop is the master-slave configuration. One way of designing it is the master-slave configuration. This is the master-slave JK flip-flop. Just for their completion of notes I am showing, but how it actually becomes an edge-triggered device, I have taken detailed session on it. Okay, but right now derivation, no time. Okay, so you can watch any of my earlier session, what flip-flops are, how flip-flops are edge-triggered, and how this cascade combination, this is known as master, how a cascade combination of two latches, this is a master latch. We connect two latches in cascade and feed them with complement clock. Okay, so if this is getting the clock CP, this is getting the CP complement, dhyan dena. So both are not active at the same time. Both are not active at the same time. Okay, if the master is active, slave is disactive. If the master is disactive, then the slave is active. When we draw the proper waveform diagram for it, we get a device which is only responding to the edge of the clock. This one is actually going to be negative edge triggered. This one is going to be negative edge triggered. Okay, chalo. Now the graphic symbol slightly changes, right? If it is an edge triggered device, we use a triangle at the clock input. We use a triangle at the clock input. The triangle at the clock input represents that it is an edge triggered device. It is a flip-flop. If it is only triangle, it is a positive edge triggered. If it is a triangle with a bubble, it is complement, negative edge triggered. Negative edge triggered. Okay. Negative edge triggered. Chalo. Now, with respect to flip-flops, one more case you should know how to draw the state diagrams, especially when a flip-flop is included with some combinational circuitry. So here again, there is no formula, but I have to just show one of the techniques of solving this. Okay. With flip-flops, commonly one case is given some logic circuitry and then you are asked the state diagram. Okay. So what to do in that case? So let us analyze this circuit first of all. Let us analyze this circuit. Okay, what is the flip-flop? This is a D flip-flop used here. Acha, for a D flip-flop, what is the next state, guys? Q plus, that is equal to D. Okay, from where D is coming from? D is coming from the output of a NAND gate. Let us say that NAND gate is equal to the X. Let us say that NAND gate is equal to X. Okay, right. Now, what is the output of this NAND gate? This is using the current value of the output of the flip-flop, and this is the output of a multiplexer. Let's say this is Y. Okay. So guys, for such case, there is no formula. That is why I'm not revising in the form of formula. There is one technique and specially taken a gate question to make you understand this technique. Now mux, just now we today revised the mux also. What is the output of this mux? It now depends on the input A, right? If the input A is equal to 0, mux will select the input line I0. If A is equal to 1, the output of the mux will be I1. Dear, what is there at the I0? I0 is the complement of the Q. And what is there at the I1? Isko dekh lijiye ek baar. At the I1, you just have the Q. You just have the Q. So I1 is equal to the Q. That's it. Okay. So now we have the Y also sorted. What is the output of the NAND gate? X into Y. Sorry. Q into Y NAND. Q into Y NAND. What is the value of Q? Abhi dekho, there are two conditions coming up. It may be Q bar or it may be simply Q, depending on the input line. Right. So Q into Q bar is 0. 0 ka complement hua 1. Q into Q is Q and its whole complement is simply Q bar. अब बोल दीजिए, we have got the x and simply q plus is equal to d, d is equal to x. So you have the next state equation also. You have the next state equation also. Q plus is d, d is equal to x. X is what I have derived. So let me only write down the result. This is 1 for a equal to 0. For a equal to 1, it is equal to how much? Q bar. This is first of the case. So पूरा detail में explain किया. Now what is the state transition diagram? There is only one flip flop and one flip flop has two states, set or reset. Set or the reset. This is the reset state. This is the set state. Okay. Now, if the input is 0, dear, if the input is 0, next state is always 1. So next state transition always has to go to the set. If the input is 1, if the input is 0, the next state is 1. If you are already into set, remain in the set if the input is 0. Next क्या होगा? If the input is 1, next state is toggle. This is the toggle condition. So if you are in 0, then also you will complement. But for the same type of transition, why to show two arcs? यहीं पे input को comma करके लिख देंगे. Just write down 0, 1. But if you are at 1, then you toggle and you come back to 0 if the input was 1. So if the input is 1, you have to toggle. See, this is an option. This is an option. You can take two arcs also. But commonly we should avoid that. So what is the correct answer, dear? What is the correct answer? Have a look into the options. Sorry. What is this happening? What is this happening? What is the correct answer? So this is what I have explained you. This is the technique of solving it. Okay, whenever the input is 1, have a look into this. Whenever the input is 1, there is a transition. For input 0, you go to the same set state. Answer is C. That is what I told you actually here. Dekho, whether the input is 0 or 1, look into this transition. Whether the input is 0 or 1, right? I change the state. Okay, so I go from 0 to 1, whether the input is 0 to 1. So you may take two arcs, or in short, you can avoid any one arc and write down the input here as a comma. That comma specifies that whether the input is 1 or 0, you are going to show the same state transition. You are going to have the same state transition. Okay. So there is a technique of drawing the state diagram. There is no formula. So I have explained that technique through one question. Okay. Let us also review some points about the counter, especially covering both synchronous counter and the ripple counter. Okay, synchronous counter in which all flip-flops are using the common clock, and once again there is no formula. There is a technique to design synchronous counter. So let me explain you through technique through one example. Design a 3-bit synchronous up counter. You can design a down also. I'm just taking an example. 3-bit synchronous up counter using T flip-flops. Okay, using the T flip-flop. अब देखो यहाँ पे using the T flip-flop. तो ध्यान देना, right? 0 0 0 0 0 1 0 1 0 0 1 1. That is what is a regular 3-bit up counter, na? 0 1 2 3 4 5 6 7. After it reaches 7, repeat. Unless and until you power off, it is going to repeat. That means up till the power is applied to this particular circuit, it is going to count 0 to 7 and hence repeat. After 7, again 0, right? And etc. 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 Look at the transition, look at the excitation table and the complete transition table also. Dekho, if it is, look into this, this is the current state. If it is 0 0 0, the next state will be 0 0 1, isn't it? If it is 0 0 1, the next state will be 2 0 1 0. Okay, so corresponding to every current state, I have written the next state. 0 ka likha 1, 1 ka likha 2, 2 ka likha 3, 3 ka likha 4. If the current state is 7, guys, what is the next state? For the current state of 7, next state will be back to 0. So I have written here is 0 0 0. This much I have written. Now let us fill this. Normally, till this time, latches or flip-flops were given. Based on the input of the latch, or based on the input of the flip-flop, you are able to write what is going to be the next state. But here, guys, the next state is given to you. What should be the input of the flip-flop to achieve that next state? Right? Deriving the input of the flip-flop, okay, when the current state and next state combination is given, that is known as what? That is known as the excitation table or excitation signal. Okay. So understand this. ये समझना जरूरी है. This is simple. This is transition is simple because we know 0 के बाद 1 आएगा, 1 के बाद 2 आएगा, because we are designing a up counter. But how to write down the input of the T flip-flop to achieve this state transition. Understand this. Understand first Q2, everybody. Understand Q2. 0 to 0. The output of the which flip-flop we are designing using T flip-flop. Output remains the same. That means what? Output remains the same. That means the T input should be 0. Because if the T input is 1, output should toggle. Next, again 0 remains 0. Again 0 remains 0. ठीक है, तो T input should be 0. यहाँ देखेंगे, this 0 now becomes 1. Everybody, in this particular row, Q2 was 0, now it becomes 1. That means it is toggled, and it will toggle. The state of the device will toggle if the T input is 1. So here, T input should be 1. Then only such a transition will occur. Right? Chalo, great. Now look into the next. Right? Itna हमने कर लिया है. Now look into the next. 1 to 1, sir, same. 1 to 1, same. 1 to 1, same. Same hai to keep writing 0 at the T input. Look at the last. 1 to 0. Look at the last. It is a change from 1 to 0. That is again toggled. And the device will toggle only if the T input is 1. Only if the T input is equal to 1. Next बोलिए तो. Next बोलिए. Similarly, we will write down for Q1. So Q1, 0 to 0, same. 0 to 1, toggle. Okay, now 1 to 1, same. 1 to 0, toggle. So same and toggle. Again, guys, once it is same, then it toggles. Next cycle, same, then it toggles. So alternate 0, 1. Got this? Alternate 0, 1. Yes. Next, let us look at the Q naught. Let us look at the Q naught. Okay, Q naught. 0 to 1, 1 to 0. 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 Every time it just toggles, 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 toggles. Okay. Every time it just toggles, 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 toggles. So T input is always 1. ठीक है जी? T input is always 1. T input is always 1. T input is always 1. Now, what is the next step? Normally, we'll follow the K map. Okay. देखो, what is the TQ0? इसके लिए K map का need नहीं है. TQ0 is always 1. TQ0 is always 1. That is fixed. This is simple. But what about TQ1? Okay, we are not deriving. Okay, whatever is the result from K map, I will just tell you. Okay, what is the TQ1? This alternate 0, 1 pattern, this is going to give you the value of Q0. This will be equal to Q0. Okay, next, what is the TQ2, the T2 input? And that is the product of Q0, Q1. That is going to be the product of Q0, Q1. And this is what is implemented here. Dhyan dena. Right, this is little bit mismatched. Let me write down here. Okay, this is TQ2, this is the MSB, okay? This is LSB. This is TQ0. What is TQ0? It is always 1. Now dhyan dena. Right, what is TQ1? TQ1 should be equal to the Q0, and that is the connection shown here. This is Q0, this is Q0. Correct. What is the TQ2? TQ2 is product of Q1, Q0. It is the product of here Q1, here Q0. To take their product, I have taken the AND gate, and this comes here TQ2. Right. This is Q1, Q0. Correct. Chalo. What is the logic circuitry? For a 3-bit synchronous counter, what is the logic circuitry? Of course, 3-bit hai, so for every bit we need 1 flip-flop, so 3 flip-flops plus 1 AND gate. Suppose dear, if you are designing, a 4-bit up counter. Suppose you were designing a 4-bit synchronous up counter. Without writing any table, let me give you the results. TQ0 same आएगा 1. TQ1 will be same as Q0. TQ2 will be same as Q0 Q1. TQ3 4-bit. Now the fourth flip-flop will also be active. Okay, the input of the fourth flip-flop TQ3, the input of the fourth flip-flop TQ3 will be Q0, Q1, Q2. The product of all the Q before 3. If you are calculating TQ2, it is the product of all the Q before 2. चलिए बहुत ही बढ़िया. This is what is the answer. Now, does it mean that you need a 3-input AND gate? No, you don't need a 3-input AND gate, because this can be written like this: Q0, Q1, Q2. Q0, Q1 तो बेटा already निकाल दिया है, right? There will be one more product with the Q2. There will be one more product with the Q2. This will be the next flip-flop, and then it becomes a 4-bit design. Got this? So again, what you need in addition? What you need in addition is a additional AND gate of 2 input capacity only. I don't need a 3-input AND gate. I don't need this 3-input AND gate. Got this? Because Q0, Q1 is already derived. So what is the hardware? What is the hardware in general? What is the hardware in general? Right? If I want to talk about the n-bit synchronous counter. Guys, again some formulas coming up here. Arey yaar. N-bit synchronous counter. Okay. What is the total hardware required? 2 formulas I will give you. Hardware was important to show, so I have shown you. The hardware consists of n flip-flops. Every bit requires 1 flip-flops plus some AND gates. How many AND gates? How many AND gates? देखो 3-bit के लिए you have only 1 AND gate. 4-bit के लिए you will have 1 more AND gate. That is total 2 AND gates. In general, n minus 2, 2 input AND gates. AND gates, that too of 2 input capacity. N minus 2, 2 input AND gates. N minus 2, 2 input AND gates. N minus 2, 2 input AND gates. It is n minus 2, 2 input AND gates. ठीक है? That is what is the answer. अच्छा. What about the delay? The propagation delay is given by T clock to Q or T flip-flop. I'll explain you this. मतलब no need to derive and no need to understand with timing diagram, just the formula is required because questions इस पे आ जाता है. So what is T flip-flop or T clock to Q? Is the propagation delay of, it is the propagation delay of each flip-flop, which is the same. The propagation delay of flip-flops will be assumed as same. All flip-flops are identical. So the total propagation delay is equal to the propagation delay of single flip-flop. The simple logic is, without drawing the diagram, without drawing the timing diagram, because it is a synchronous design, all the flip-flops are active at the same time. All the flip-flops are active at the same time, right? So whatever time this takes, at the same time, this is also active, at the same time, this is also active. So all will produce the output at the same time. Okay, just I have neglected the delay of this AND gate, and that is actually negligible only. In front of a flip-flop, the delay of a simple AND gate is just tending to 0. Okay, so all the flip-flops are active at the same time. When do they produce the output? All will produce the output at the same time, and that is the TFF. That is the TFF. That is why total delay is also equal to TFF. Okay, these are 2 important formulas. Similarly, what is this formula for ripple counter? वो भी मैं आपको बताऊंगा. Okay, ripple counter. Okay, in a ripple counter, the flip-flop output transition, the output of every flip-flop. See, in the synchronous counter, all the flip-flops are connected with the common clock. But in ripple counter, it is not the case. The clock is connected. The clock, external clock, main clock is applied to the LSB flip-flop. And then the output of every flip-flop is connected to the input of the next flip-flop. Yeah, ripple is a kind of asynchronous only, na? Right? Have a look into this. This is not complete. Okay, let's understand. This is the circuit diagram of 3-bit ripple up counter using T flip-flop. Right? Using JK flip-flop. Using JK flip-flop. Okay. Okay, Ravi. Okay. Now, if it is a 3-bit ripple up counter using JK flip-flop, have a look into this. This is the external clock applied to the LSB, right? Applied to the LSB. This is the J0 and K0 input. This is the J and K input of the next J1, K1. This is the J2, K2. So this is the output Q0. This is Q0 bar. Q1 and Q1 bar. This is Q2 and Q2 bar. To design a ripple counter, whether it is JK or T flip-flop, all the flip-flops should be in the toggle mode. Let me write down one important point here. All flip-flops must be in toggle mode. Dear, what is the meaning of the toggle mode? All the flip-flops must be in the toggle mode. What is the meaning of this toggle mode here? What is the meaning of this toggle mode here? Toggle mode means when J and K. What is the toggle mode of JK flip-flop? When does the JK flip-flop toggle the state? When both the JK inputs are 1, 1. When both the JK inputs are 1, 1. So all the JK inputs of all the flip-flops will be 1, 1. You don't have to worry about the inputs. You have to just fix it as 1, 1, 1. Okay. Look into this. The external clock is applied to the LSB flip-flop. I have taken negative edge triggered devices here. Then the output of every flip-flop becomes the clock of the next flip-flop. The output of the next flip-flop then goes to the clock of the next flip-flop, and so on and so forth. And so on and so forth. Isn't it? And so on and so forth. Correct. Now, when we actually see the count, no need to derive, no need to solve in detail, but this is going to give you the count which is that of a up counter 0, 0, 0, 0, 0, 1, 0, 1, 0. Only one connection change. Suppose I take the clock as positive edge triggered. Okay, this will become a down counter. Or I'll write down this configuration. Or if you take the clock not from Q0, from Q0 bar, it again becomes a down counter. So you have to just remember this. This is the technique. This is the shortcut I will write down. This is a shortcut I will write down. Here the connection of the clock is. Here the connection of the clock is from the Q output up to the negative edge. This is the Q output to the negative edge. Right. This is what is clock connection. Q output to negative edge. Based on the clock connection, you can just see and identify and tell the type of the counter. What is the type of counter? I have told you it is the up counter. Okay. Suppose, dear, if you take Q to positive edge, right? See, ऐसा मान लीजिए, if any one of the parameter changes, the type will change. Q to positive edge, this becomes down. So what you have to do, guys, remember only one thing. Remember only one thing. Q to negative edge is up. Just feed this in mind. Very, very important. Q to negative edge is up. So Q to positive is down. Acha. If it is Q bar, dear, if this is Q bar to negative edge, if this is Q bar to negative edge, then what is the result? See, negative edge remains as it is. Q to Q bar. One change, the type changes. Up again becomes down. Up again becomes down. Right. Next, Q bar to positive edge. Only see with reference to 1. Isko bhul jao, isko bhul jao. Only see with respect to the first. Right. Q to negative edge. Q bar to positive edge, both changes. Up to down, down to up, 2 times change, na? So this has to be down. This has to be down. So you can simply remember 1 point. You can simply remember 1 point, right? You can simply remember 1 point. Q to negative edge is up. Q to negative edge is equal to up. Q to negative edge is equal to 1. Okay. Yeah, there is one more technique. See, this is also very simple. Yeah, there is one more technique, right? Okay. ऐसा भी मान सकते हैं. Let's say Q is equal to 1. Q bar is equal to 0. Let's say negative edge is equal to 0. Positive edge equal to 1. Okay, if I just assume normal is equal to 1, complement is equal to 0. If I assume this, so see, this is Q, which is 1 into 0. 1 into 0 is 0. Yahan pe mila up. Right? 1 into 1. Q is 1, positive is also 1. Here I get down. Right? Q bar to negative. Right? What is Q bar? 0. Right? What is negative? That is also 0. 0 to 0, I get 0. This was also down. Right? What is the last? What is the last? What is the last? देखो last हुआ Q bar to positive. That is 0 into 1. तो ये तो कोई gate नहीं बना. But the simple logic is Q to negative and Q bar to positive. What type of gate? Q bar to positive. Q bar to positive. Sorry, this is up. Typo error, guys. That is up, up, up. Up, up, up. Sorry, that was a typo error. That was a typo error. ठीक है. अब आप यहाँ पे देखिए. Right. Q to negative. Okay, 1 and 0. Up कहाँ पे आ रहा है? अरे come here. When you are getting the up at the 1-0 combination or 0-1 combination. 0-1. That is the XOR gate. Right. Up counter is obtained at the XOR possibility. Up counter is obtained at the XOR possibility. ऐसा याद रख सकते हैं. This is one more way of remembering it. Right? XOR possibility when both are different. Q to negative edge or Q bar to positive edge. When both are different, you get up. When both are same, Q positive, this is also true, this is also true, you get down. Q bar to negative, this is also false, this is also false, 0, 0, you get down. So XOR पे down मिलेगा, XOR पे up मिलेगा. ठीक है? This is one more way. Or even the first method I told you is also simple. Q to negative edge is up. Q to negative edge is up. इतना याद रख लीजिए. Any one parameter changes, the answer changes. The type changes. Okay. The type changes. Acha. One more important point to mention here before I show you. Yeah. The next point to discuss here. Okay. With respect to a n-bit ripple counter, dear. With respect to a n-bit ripple counter. Hardware, as I told you for synchronous, same I have to give you the result here also. Here the hardware is only n flip-flops. Here the hardware is only n flip-flops. But the speed, यहाँ मैं delay की बात करूँ, more delay will correspond to less speed. The delay will be n times t clock 2q. Right? Or n TFF. It is n times the delay of one flip-flop because one by one the flip-flops will be active. One by one the flip-flops will be active. It is a ripple design. Na? Once the LSB, clock is only applied to LSB. Once this completes the calculation, when it produces the negative edge, then this is active. So TFF completed. Then this performs the calculation, one more TFF. Then this is active. Up to 2FF, this is disactive. Then it performs one more calculation, total 3 TFF. Total kitna hua? 3 TFF. Right. So if it is n flip-flops, it will be n times TFF. If it is n flip-flop, n type. Very slowly and very quickly and roughly I am explaining you. Okay. So it is n TFF. Okay. So what is the comparison between synchronous and ripple? What is the comparison between synchronous and ripple? Clearly ripple is taking more delay, more time. ठीक है? Right. It is slow, more delay. Right. Synchronous, less delay, so it is fast. ठीक है, but this is fast, but it takes more hardware. What was the hardware of synchronous? Same n flip-flops, but additional AND gates, right? The fast plus fast, but more hardware. It is a simple logic in the world. It is always a simple universal fact in the world. To obtain better performance, you have to pay more. More hardware means more cost. More hardware means more cost. Slow and less hardware. Here, this will take less cost. This will be cheap, but at the same time, it is slow. This is the comparison. This is a simple comparison. Now, with respect to ripple counter, up and down, I have explained you. But what is the type of question? Again, no formula, but type of question. In the ripple, what is more important? Up and down configurations I have explained you, but what is more important is the question based on reset pin. ये discuss करना पड़ेगा. Question based on reset pin. Okay, there is a circuit diagram shown to you. Okay, this circuit consists of JK flip-flops, each with the active low, asynchronous reset. I'll explain you this with the question. What is this circuit? Modulo. What is the meaning of modulo? Modulo, total number of states. Total number of states and total count number. Total number of states and total count number of the device. Okay. What is the modulo? What is the count number of this particular device? Have a look into this device once again. First of all, identify the type of connection. See, all the JK flip-flops are in the toggle mode. All the JK inputs are 1. See the type of connection. Q to what type of clock? Negative edge. Q to negative edge. Very simple. The connection is Q to negative edge. Right? 1, 0. Different combination. Different means XOR. XOR pe up aayega. This is a up counter. Q to negative edge is up counter. Q to negative edge is up counter. This is a up counter. Suppose, forget this reset. Dear, forget this reset. If there was no reset, this is a regular up counter as I've already taught you. That is what the same thing I told you. If there was no reset, then the count is 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. up to 1, 1, 1. After that, back to 0, 0, 0. What will be the mod number? What will be the mod number then? Then it will be mod 8. It will count, it's a 3-bit counter, na? 3-bit has 8 combinations. It will count 000 to 777 and repeat. It will be a mod 8 counter. Tab to koi problem hi nahi hai. It is going to be a mod 8 counter, dear. It is going to be what? It is going to be a mod 8 counter. It is going to be a mod 8 counter. But that is not true, because here there is a reset functionality. What is the type of reset functionality given? Active low asynchronous reset pin hai yahan pe. There is an active low asynchronous reset. First of all, what is the meaning of active low? We all know. And it is represented by the logic symbol also. I told you now what is the logic symbol of active low. It may be bubble at the input or it may be bar at the variable. So RD bar. R bar means active low reset. It will be active once it receives the low signal. For it to be active, for it to work, it should receive the low signal. It should not receive the high. तो यहाँ पे 0 आएगा तो ये काम करेगा, right? What is the meaning of asynchronous? Asynchronous here means it is not synchronized with clock. It will work independent of the clock. It will work independent of the clock. Understand this first of all. Active low. Understand this. Active low asynchronous reset. It means the flip-flop will reset, right, if RD is equal to 0. That is what is the meaning of active low. Once you send the low signal here, flip-flop will reset. But when it will reset? It will reset immediately, almost immediately, right, without waiting. Without waiting. Without waiting for the next clock edge. Without waiting for the next clock edge. without waiting for the next clock edge. ठीक है, without waiting for the next clock edge. It will reset immediately without waiting for the next clock edge. बहुत ही बढ़िया. ठीक है. So now let us understand this. Okay. So when it is going to receive 0, the reset pins is obtained through the output of this NAND gate X. X comes here. Okay, the X comes here. Right. Right. What we need, X is equal to 0. X is equal to 0. Output of NAND gate is 0 when both the inputs are 1, 1, when both the inputs are high. So X is equal to 0. If both Q2, this is the input Q2, ये input कहाँ से चला आया? This is the input Q0, right? If Q2 and Q0 are both equal to 1, then only the output of NAND gate is 0. The output of NAND gate is 0 if both the inputs are 1, 1. If both the inputs are 1, 1. Q2 and Q0 are both equal to 1. Right? Chalo, so let us wait for this. Let us write down the sequence Q2, Q1, Q0, what actually is happening. Right? So this is 0, 0, 0. Right? Both should be 1, 1. हमें इन दोनों का wait करना है. Both should be 1, 1. Otherwise, it keeps counting up. It is the up counter. So next is dear 0, 0, 1. Next is 0, 1, 0. Next is 0, 1, 1. Next is 1, 0, 0. Here also both are not 1. Now next is 1, 0, 1. 1, 0, 1. 1, 0, 1. Both Q2, Q0 are 1. Okay, here you have X is equal to 1. Here, sorry. Here you have X is equal to 0. And since you have active low reset pin, as soon as you receive low, it is going to reset the flip-flop. Reset means 0, right? It is going to reset which flip-flop? Sir, it is connected to all three. So it is going to reset all three flip-flops, right? All flip-flops reset, okay? And then what is the next state? If all flip-flops reset, so all are 0, 0, 0, next state is 0, 0, 0, right? Next state is 0, 0, 0. Now what is the count sequence? Everybody, what is the count sequence then? Dear, what is the count sequence? The count sequence is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Nah. See, 1, 0, 1, as soon as 1, 0, 1 appears, the reset becomes active and all flip-flops reset without waiting for the next clock. Without waiting for the next clock. That is what was the meaning of asynchronous. That means this state will appear and diminish. It will appear and vanish away. आएगा जाएगा पता ही नहीं चलेगा, just a blink of a moment. So we will not count it as a valid state. We will not count it as a valid state. Are you getting it? We will not count this as a valid state. We will not count this as a valid state, right? So the only valid state is up to 1, 0, 0, and then it is 0, 0, 0. Repeats. Then it repeats. Okay. Then it repeats. Only 0, 0, 0 to 1, 0, 0. So what is the mod number then, dear? What is the mod number? 0 to 4. Mod number is 5. How many? Mod number means total number of states. So this is mod 5. Mod 5. Everybody. This is known as mod 5 counter. This is known as the mod 5 counter. This is known as the mod 5 counter. ठीक है, बहुत ही बढ़िया. This is known as the modulo 5 counter. Modulo 5 up counter. So let us select the correct option. It is modulo 5 and that to up counter. Modulo 5 up counter. So one thing is identify up down. Next is mod number. अच्छा, one more thing. If it was a synchronous reset pin, ये भी include करेंगे यहाँ पे, right? If reset pin was synchronous, then your answer will be, what is the meaning of preset? Means the device will be set to 1, 1, 1. The device will be set to 1, 1, 1. Reset is setting to 0. Not necessarily all 1, 1, 1, depending whatever flip-flops are connected to the preset. Reset means 0, preset means 1, poly. Okay, only that is the difference. If the reset pin was synchronous, then what is the count sequence? Then what is the answer? Then dear, what is the answer? Same circuit diagram, okay, same circuit diagram. The count sequence will be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Now 1, 0, 1 comes. Listen to me carefully. 1, 0, 1 comes, due to which X becomes 0. X becomes 0, so all the flip-flops will be reset, but not immediately. All the flip-flops will be reset in synchronization with next clock. That is what is the meaning of synchronous reset. All flip-flops will be reset in sync with the next clock. That means I can say that 101 will be active. 101 will be active up to the next clock cycle. 101 will be active up to the next clock cycle. So it is a valid state. That will also be counted. Any state which is active for one clock cycle is a valid state for me. So 101 will be active up to the next clock cycle, and hence it is counted. Hence it is counted. Hence this is counted. And hence it is going to be mod 6 then. Right. So there will be a difference of 1 in both the answer. You have to be very carefully reading the question, whether the reset pin is synchronous or asynchronous. If nothing is mentioned, by default asynchronous. If nothing is mentioned, by default asynchronous, dear. Right. Chalo. Right. What is the frequency at Q3? What is the frequency at Q3? Next case. Q3 means Q3 is MSB here. So one more formula to be added here. Look into this. Na? Q3 is MSB, guys. And what is the frequency at MSB bit? It is the applied clock frequency, external clock frequency, divided by the mod number of the counter. Divided by mod number of the counter. N is equal to the mod number of the counter. N is equal to the mod number of the counter. N is equal to the mod number of the counter. Okay? Q0, Q1, Q2, Q3. Now, again a reset is given to you. This reset is derived using X. Let us understand this question once again. Okay, this is output of NAND gate X, and it goes to all the flip-flops, right? Here, X is equal to 0 if both the inputs of the NAND gates. What are the inputs? One is the Q1 and one is the Q3, right? If both Q1 and Q3, are high, if both Q1 and Q3 are high, if both Q1 and Q3 are high, so Q3, Q2, Q1, Q0, both should be high, right? Acha, what type of counter it is? What type of counter? Up or down? Simple, na? Q2 negative edge. Q2 negative edge, it is up. Q2 negative edge is up counter, we know. Q2 negative edge is up counter. Right. So it starts from 0, 0, 0, 0. Because of up, it will be 0, 0, 0, 1, 0, 0, 1, 0. कब तक wait करना है? Until both Q1, Q3 are 1. Q1 and Q3, ये दोनों 1 होने चाहिए. Okay. So we have to wait. 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1. Now comes 1, 0, 0 when the Q3 is high for the first time, but Q1 is 0. तो next चले जाएंगे 1, 0, 0, 1, 9. Next देखेंगे 1, 0, 1, 0. Next is 1, 0, 1, 0, dear. At this 1, 0, 1, 0, ध्यान देना. At this 1, 0, 1, 0. At this 1, 0, 1, 0. At this 1, 0, 1, 0. Q3 and Q1 are both high. Right, X will become how much? X will become low, right? All flip-flops reset. The next state is 0, 0, 0, 0. What is the modulus? So, what is the type of pin? What is the type of pin? Nothing mentioned. Okay, so reset कैसा लेंगे? Nothing is mentioned in the question here. So reset will be by default, if nothing is mentioned, asynchronous. right? And if the reset is asynchronous, then you cannot count this state. Reason I have explained you, just applying the method now, you cannot count this state. So what is the mod number now? Dear, 0000 to 1001, 0 to 9, right? It is actually mod 10. 0 to 9 means it is actually also known as a BCD counter. It is actually also known as 0 to 9, that is 0000 up to 1001, which are all the BCD codes. It's a BCD counter. Overall, I need the mod number, so it is a mod 10 counter. If it is the mod 10 counter, the question was frequency at Q3. Q3 is the MSB, and the formula for MSB is clock frequency divided by N. Sir, what is the clock frequency given to me? 1 kilohertz. 1 kilohertz is divided by 10. Okay, 1 kilohertz divided by 10. Answer is 100 hertz. Answer should be the 100 hertz. 100 hertz. Option number C. Answer is option number C. Correct, dear? Answer is option number D. Yes, mod 10, also known as a decade counter. Correct, Sri Lakshmi. Okay? Mod 10 counter, decade counter, BCD counter. Okay, guys. Yeah, the time is approaching 11:30 and let us stop the session. Right, so 2 parts we have covered the digital, and you know every subject contains lots of topic, and we are trying to concise it in the formula revision session, or you can say summary revision. And in the limited time we have, we are covering up the most important topics. Yeah, it is fundamentally important to first cover the most important topics. Yes, password मैं भूल गया, password बता देता हूँ. Today password is coming at the last. No problem. Today password is coming at the last. The last questions were consisting of reset pins. So let us take the password as reset. Let us take the password as reset. R-E-S-E-T. The password for today's PDF will be reset. It will be shared you in the Telegram. Okay, the same Telegram where I shared you the previous one. Okay, so yeah, in the time that we have, see, we have revised important combinational circuits, most important points of sequential circuits, that is, you know, quick review of all flip-flops and latches, their characteristic equation, characteristic table, state diagram, how to draw it, synchronous counter, ripple counter, what is the speed, what is their hardware, and especially the asynchronous or synchronous reset pin with the ripple counter. Then we have taken decoder and multiplexer based questions and their techniques to solve it up. We have taken the ripple adder, half adder, full adder cases, the code converter cases. In the previous sessions we covered everything regarding to Boolean theorem, all Boolean algebra, logic gates, their property, type of questions. Then the, you know, K-maps also different, you know, K-maps 2 variable, 4 variable, 3 variable, 2, 3, 4 variable, 5 variable also, and then don't care conditions also were included. Okay, and several other topics we discussed in the previous classes also. Okay, including all types of representation of Boolean function, maximum, min terms, and all the properties. So in this particular time, we have covered, see, most important topics. Okay, yes. I can't say 100%, but yeah, more important topics we have revised. Okay, thank you. Stay tuned. Tomorrow will be the analog circuits part 2. Let me give you the update for tomorrow also, guys. Tomorrow at the same time of 9 p.m. there will be the formula revision of analog circuits part 2. Analog circuits part 1 was done yesterday. That is going to be part 2. Okay, guys, with this I, Rakesh Talreja, sign off. Okay, you also go and again revise, keep preparing for your gate preparation. Right, bye bye, good night, stay safe and take care.